Hello and welcome to this introductory video on Kirchoff's rules. In this video we're going to tell you Kirchoff's two rules as well as provide some setting for why you should care. So let's think about a generic sort of situation where you've been asked to design some sort of circuit that hopefully achieves some task. We don't know what the task is, so we're just going to represent whatever you're trying to do by arbitrary resistors in our circuit. But let's suppose that you wanted to do maybe a few things with your circuit. So you wanted to do two things up there, and you wanted something to happen over here. And maybe for the sake of argument, let's throw in a capacitor too, just because. And we've got some batteries that's actually connected to our circuit to power whatever you're doing. Okay. Now when you build this circuit, you need to keep track of what potential differences are at each circuit element, because you want to certainly make sure that you've got enough energy to do whatever you're trying to do. You need to think about what the current is in each part, because you don't want to overload anything. So you need to be able to analyze what is the potential across each circuit element, what is the current flowing through them, and things like that. And Kirchoff's rules are the way that you do that. So this circuit, quite complicated. You don't necessarily want to go through and say what is the equivalent resistance and capacitance of this circuit in order to figure out everything that's kind of happening. And even if you did, you would then need to unravel that and go backwards and figure out what's going on in each circuit element anyway, in order to verify that your circuit is going to work and is safe. So Kirchoff's rules provide a nice sort of understanding of how you can figure out what those currents and potentials are. And they're really nice and conceptual. So the first one is something called the junction rule. In order to set that up, let's first describe what a junction is. So this here is a junction, this here is a junction, and this here is a junction. What they are is the branching points in your circuit. So over here I've got some current which is clearly flowing from the battery according to convention, right? It flows from the positive terminal, and we pretend that the positives are moving. We know really it's the electrons flowing from the negative, but the convention dictates that this is our current. So it's going to flow over here, and when it encounters this thing, it's got two choices. Some of it might go that way, and some of it might go that way. And then what is going to happen? Well, it flows across. This top branch is coming that way. There's some more current there. When we get over here, we again have some choices. We can go that way and that way. Then these guys will come into this thing, and overall come back and flow back to our battery. That is the closed circuit. But we have all these choices. So how much current goes in each branch? Well, that'll depend on the resistances, but there's also a very nice, obvious statement that we can make about this junction here. So when you think about this junction, what's going on? We have some charges flowing in, we have some current, right? And that talks about charges per second, coulombs per second, that flow through that bit of wire here. Now, whatever comes into this junction must also go out. We're not having a whole bunch of electrons get stuck in this junction. Right? This is all a conductor. The charges are free to move. So whatever comes in must go out. And that's all that the junction rule is telling us. It's a very nice, conceptually easy to understand rule that I'm basically saying I'm not storing any charges at this junction because it's not a capacitor. It's just a junction. It's all conductors. Charges are free to move. What goes in must go out. So the sum, in this case there's only one, but over here we've got two things coming in. So the sum of whatever's coming into a junction must equal the sum of all the currents that are flowing out of the junction. So this plus this is equal to this. And over here, these two things going out is equal to these two things going in. Okay? And then similarly here, these two things coming in equal to the one thing going out. That's all that the junction rule tells us. So we can talk about, if we call that I1, and that I2, and that I3, then we know that the sum of those, I2 and I3, let's label them just for completeness, then we can write down things like that I1 is I2 plus I3. Okay. And that I3 would be over here too, and this is still I2. And then we would talk about maybe an I4 and an I5. And we would say, oh, I4 plus I5 must also equal I2 plus I3, because they come back together there, etc. Straightforward, very conceptual. What goes in must come out. That's all we're saying. Okay, just like water basically. If water is flowing through some pipes and it branches, we know that the total amount that's flowing in is also flowing out. The water doesn't suddenly stay at that branching point and balloon out or something. All right, so then the other rule that allows us then to complete the discussion thinks about what's going on with the potential difference across the circuit elements. And it's basically saying, look, the battery is providing energy. Whatever's going through there must be flowing nicely across the circuit elements. And if I'm providing a certain amount of energy, then by the time I get back, I should have used all that energy. Okay? And of course, we talk about energies in terms of potential when we're doing circuits. So it really amounts to saying that as I go around some loop, the potential that is provided by the battery should then be used up by our circuit elements. So if this thing has some EMF, and this thing has a potential difference, say V1, and this thing has a potential difference V2, then just looking at this circuit, I know that the EMF must equal V1 plus V2. Okay? And that's basically saying that along this bit, that part is all an equipotential surface. So is this part too, really, if we want to get specific. So we know that right up until here, if this thing is a positive EMF, then those things are at same potential, which is equal to the EMF of the battery, say, because we're not worried about the internal resistance. So these things are sitting at the EMF. Then there's some drop across here. There's another drop across here. So this bit all is going to sit at the same potential because it's all a conductor. So all of that's at the same thing. So whatever drop is here is the same drop here. So I can write that that's got to be V1 as well because it's equal potential, so they're connected. So this potential might be, well, it's EMF minus V1 officially, looking at the original resistor that we specified. So we got EMF minus V1 sitting here. All that's equipotential, which is how we know that that one also has to be V1. And we're sitting at EMF minus V1 over here and EMF minus V1 over here. And then down here, if I go across this one, I know that that's got to be EMF minus V1 minus the V2, whatever the potential difference across that second resistor is. But lo and behold, that's all again an equipotential surface. And we know that that's connected to the zero of our battery. So we know that EMF minus V1 minus V2 has to be 0, or EMF must be V1 plus V2. Okay, so that's just what the loop rule is. So we can shortcut necessarily tracking it like this through everything and talking about equipotentials. And just remember that the voltage across any closed loop, so I was just looking at this loop originally, has to be 0. I know that this loop, same thing, so that EMF and that EMF have to be 0. Which is again another way of proving that it has to be V1. I could also look at the loop, let me draw it in a different color, just for the sake of completeness. So if I was thinking about going around this way along the circuit, so this outer loop basically, well then again I know that I have V1. I can call this drop VC because I don't know what it is at the moment. And I would know that basically according to that, the EMF, because I start with the battery, has to be V1 plus VC. And then I come back around, there's no other circuit elements along this path, so this must also be true. Right, and this is then combined with my junction law enables me to figure out everything about this circuit. So that's all the rules are. They're nice conceptual statements about what must be true in the circuit. You can justify them by doing lots of details on the diagram, but fundamentally, if you just remember these two rules, they're just nicely encapsulating what has to be true. The current doesn't pile up, that's basically what the junction rule says, and you use up all the energy, that's basically what the loop rule says. Okay, so the potential drop in any closed loop must be 0, which basically means potential in by the battery to equal potential out across your circuit elements, and then similarly current in must equal current out.